Okay, so in the last class, we had discussed about the basics of FM, and we also got to know how to generate a narrow band and wideband FM. Now we shall try to see how we can demodulate the FM signal. So this block was shown in the previous video also, where you have a slope circuit as well as the envelope detector. So this is basically FM discrimination method. A slope circuit is nothing but a differentiator basically, which can also be called as a LC circuit, a tuned circuit. So we shall see the circuit diagram of it. So this is how the circuit diagram of a slope detector will look like. You apply the FM input. There is basically a transformer setup there. Now it depends on what frequency this particular LC circuit is tuned to, because based on that, the circuit is going to operate. Supposingly, if I tune this circuit to FC, let's say, FC becomes a center frequency, and this LC circuit would behave like a simple resonant circuit. And all of us know how the response of the LC circuit looks like. You can see this particular waveform, where you can see, if at all the circuit is tuned to FC, this frequency will be equal to FC. And where would FC plus delta would appear? FC plus delta F would appear somewhere here. FC minus delta will appear somewhere here. Now, will this serve the purpose? Because we say that the frequency will get tuned or changed to FC plus delta if the modulating signal reaches the positive peak value, and FC minus delta if it reaches negative peak value. This is what we say, isn't it? So, but if at all the LC circuit gets tuned to FC, what happens is, as and when the input is applied, that is the modulated signal is applied, the change in the frequency will make the amplitude to basically get reduced, isn't it? And similarly, the reduction in the modulating voltage will see the reduction in the frequency, which again makes this circuit to give an output where the amplitude reduces. So for both FC plus delta and FC minus delta, the amplitude is going to reduce, which is not a good thing. So that is why the circuit is always tuned to what is FC plus delta. So if you are tuning it to FC plus delta, what happens? When the frequency arrives at this circuit, slope detector, as the circuit is already tuned to FC plus delta, if at all you are starting the waveform from FC, which is zero modulating signal, obviously the voltage what appears at the output will have a voltage which is in between FC plus delta and FC minus delta. So as and when the frequency increases towards FC plus delta, what happens? The amplitude increases. This is what we expect. As and when the frequency increases, modulating signal voltage should also be raising. So this is kind of reverse process of what we did in the frequency modulation block. So when basically FC comes back to FC minus delta, the amplitude reduces because it is at this particular point, FC minus delta. So this is FC plus delta. This will be FC point. That will be FC minus delta. So what you see is a linear curve which shows an increase in the voltage as well as the reduction in the voltage. So this is what we are expecting. So this is how basically this circuit is going to behave. And once this LC circuit operation is over, that is at this point, if you observe at this point, after this operation, what you see is basically an envelope detector. This envelope detector is nothing but a demodulation circuit. Now if you come back to this, what you observe at this point is a waveform which is amplitude modulated kind of thing, isn't it? So the amplitude of the carrier, anyways the frequency is changing there, but the amplitude is also varying because of the slope detector operation. Now this kind of input is what is used in the envelope detector. So envelope detector will basically take care of the actual demodulation process which has to happen, and we'll be able to get back our message signal. Now this block diagram basically speaks about a balanced frequency discrimination. So this is something like a two-fold circuit which was earlier discussed for the slope detection. Okay, why do we require it? When you observe the frequency response, we have written a very linear response at this point. If you see the slope of these two, on the either side of FC plus delta, the response looks more linear. But in the practical scenario, this is not the case. You will have a very non-linear response as far as the LC circuit is concerned. So when there is a non-linearity existing, obviously the waveform what we get at the output of the slope detector will not be actually the modulated envelope. So in that case, we will lose out the information. So we have to safeguard the information, and for that reason we go for a two-fold network like this, where we use two slope detectors. One, the above one will be tuned to Fc plus delta, the below one will be tuned to Fc minus delta. So you will have two different tuning circuits to basically fetch out the signal properly. So the process will remain the same, the operation of the circuit will remain same, but the advantage of going for two-fold is the non-linearity reduces. So this is how we can take care of it. And this will be the actual circuit of it. So what you observe is the same circuit but tuning to different frequencies as such. And this is the frequency response of it. So you can observe what is happening at Fc plus delta and Fc minus delta. The same response, but we have tilted the response because Fc minus delta is appearing at the bottom. Okay. What are the advantages of the circuit? The circuit is more simpler. The circuit is more efficient than simple slope detector. It has better linearity than the simple slope detector. The major disadvantage is it is always difficult to tune, since the three tuned circuits are to be tuned at different frequencies. Input is tuned at Fc, and then you have Fc plus delta for the above one, Fc minus delta for the below one. Amplitude limiting is not provided in this case. So this is also one more important disadvantage. Moving on to the next kind of FM detection, we've got what is called as a zero crossing detector. So this detector basically exploits the property that the instantaneous frequency of an FM wave is proportional to delta t, which is the time difference between adjacent the zero crossings of the FM wave. T is chosen in such a way that the zero crossing detector operates on the principle that the instantaneous frequency of an FM wave is approximately given by Fi, which is equal to 1 over 2 delta t. So probably we'll take an example here. So this waveform is what is written. We'll take a window capital T, and capital T value should be in such a way that it should be larger in comparison to Tc, which is nothing but 1 over Fc, that's the carrier frequency or the period of the carrier signal. So this capital T value should be far greater compared to Tc, and at the same time it should be very small in comparison with Tm. So it should not be occupying the entire modulating signal period. It should be very small. So the window should be aptly selected. And we define one thing which is called as delta t, which is the spacing between the two zero crossings, adjacent zero crossings. So based on that, we can define what is called Fi, which is equal to 1 over 2 delta t. So this becomes obvious. You try to take the four adjacent zero crossings, number 1, 2, 3 and 4. You can see that. If you see within the duration capital T, you can see 6 number of zero crossings happening, starting from the first one, second, third, fourth, fifth and sixth. So 6 zero crossings are happening, or you can just say it is only 1, 2, 3, 4 zero crossings. It all depends on how we our perspective. So based on that, you can define what is Fi equal to. Now what do I get out of Fi is, we'll be able to understand that Fi is basically tracking the change in the frequency, that in turn will give me the change in the amplitude of the modulating signal. How we shall try to see.